Welcome back to ECE 442-542. The next time we meet in this classroom will be exam number 1. Hopefully that's not surprising too many people. Homework number 2 is due today or this evening by 11:59, and that includes not only a problem piece, but also a MATLAB piece. Don't forget to include the MATLAB piece. Talking about homework, I have yet to get a grader going on the homework problems, and for that reason, I hope you can look and compare your homework to the solutions to the homework, and in the future, when the grader does grade your homework, if you could get a perfect score on your homework and still miss half of the problems, meaning some of the homework may just be an attempt. The grader may not grade that particular problem. So now we're doing a little probability, a flip of a coin as to which problems get graded and which ones do not. I'm basically telling you, don't be misled if you get a 10 out of 10 on the homework and you actually have some of the problems worked incorrectly. Some of the problems may just be being examined that you submit for being attempt. Some of them may be actually graded. And so it's sort of a random selection process as to which exams or which homework problems are graded and which ones are attempted. But I hope that's clear. If you get a 10 out of 10 on a homework, don't assume going forward into an exam that what you did on the homework was exactly correct. It may not be. Any questions? All right. There is, yes? Am I going to, the question was, am I going to flip a coin to decide which problems I grade on the exam? Depending on my frame of mind, maybe I will, but don't count on it, no. I'll be grading each and every problem, fortunately. So you need to make sure and do well on your exams, which is why we're having an exam review tonight, right after or at 7 o'clock in this room. The material for exam number 1 is available on D2L. There's previous exams or practice exams, and only focus on those exams that have problems identified. If it's looking at exam 2 from a previous semester, I may have covered topics in a different order in that semester, and if I say exam 2, problem 3, just focus on problem 3 of exam 2 in that particular semester. Other problems on that exam, you may have no clue what I'm even asking. I don't want you to get confused. We'll get there eventually, but not for exam number 1. Today, or this afternoon, our goals, yes. The review is hopefully going to be recorded if the equipment cooperates. It's planned to be recorded. If not, I'm going to be even later this evening. I'll go into my office and record there if it isn't working at 7. And then, who knows, I may just be going to bed at 3 a.m. and not waking up at 3 a.m. Other questions? So we'll talk about the process of exam number 1. We'll cover again what we talked about in a hurry at the end of last lecture on the frequency response of h of z. How do you find that without actually computing the entire or the complete solution? We can now work with the transfer function and examine it on the unit circle, and we'll figure out where on the unit circle we want to find that complex number, and that will then adjust the system response to a particular sine wave or a cosine wave. Then we'll start looking at inverse C transforms, which involves the region of convergence, and that's new material. We won't be doing inverse C transforms on exam number 1. but we will possibly be doing frequency response information or using a frequency response for exam number 1. So we're sort of splitting this lecture in terms of what is and isn't covered. The process for exam 1, there's sort of a is and an is not, or an allowed and an allowed not, or not allowed. What you can bring is 1 sheet of notes, and that's on a normal size piece of paper, front and back, and a Z-transform table. And I think there's a Z-transform table on the website. You can bring that. So you'll have 2 pieces of paper, unless you just want 1 front side of notes, and then you could put your notes on the back of that Z-transform table. It's up to you. But you are allowed front and back of 1 page of notes and a Z-transform table. Then the calculator, whoops, HP, what's the one that's sort of equivalent? Is that HP 51? I was going to look at, okay, so I was thinking that I forgot to go look at my HP to see what it had on the front, but I think it's the 51. So that series, up to that, I don't want you bringing a mini computer disguised as a calculator. So we don't allow computers, and something to write with. I don't know what that parenthesis on the instrument means, but we'll get rid of that. What's not allowed or do not bring: a computer, a friend, a cell phone, textbooks, class notes. Those aren't allowed. Yes? It's implied. The question was, a friend is not on the list. You have many friends in this classroom, but before and after the exam, okay? So you can exchange fist pumps or high fives with anyone you want before the exam starts, but once the exam starts, you're on your own, okay? Was there another question somewhere? Is it clear on what's happening for exam number 1, the process? Let's talk about what we talked about last time in a hurry, and this is somewhat picture driven, or I want you to start seeing more than just a hypotenuse, but a hypotenuse is going to be important in this class also. This radial distance from the origin to your pole location. If we are interested in a frequency response, in the continuous time case, we were walking along the j omega axis in the complex S-plane. We were walking up what I have highlighted in yellow, and if we wanted to find how that particular system influenced a sine or a cosine at a given frequency, we would walk up that imaginary axis to that frequency location and evaluate the transfer function at that particular point or at that frequency. We would evaluate h of j omega 1, and that would give us a complex number. We do something similar in the z-plane, except now we know this relationship between z and s. We know z is equal to e to the st, because z is a unit advance. And if we have 1 sample period or 1 unit of time, that's capital T, and that's an advance in the continuous time setting. In the frequency case is e to the st. We know then that z and s are related by this mapping or relationship. Z is equal to e to the st, which now we want to evaluate h of z. Z is a complex number, but now we evaluate that at, like h of j omega in the s domain, now it's h of e to the j theta. And theta is the angle location, or the angular location on that unit circle. If somebody now injects a discrete time sinusoid, a cosine or sine, at a particular angle, theta of n is in the argument of the cosine or the sine, then you can find how that particular system will influence that sine wave based on the complex number you obtain when you evaluate that transfer function at that particular point on the unit circle. The stability boundary in the S-plane was the imaginary axis. The stability boundary in the Z-plane is the unit circle. Those are the corresponding locations or regions between the S-plane and the Z-plane. Which, in the continuous time case, here's the S domain or the frequency domain block diagram. We have the input E sub I, it's a sine or cosine. Our system H, which could be a filter, it could be a system, which that system could be an electrical system, a mechanical system, an electromechanical, a thermal system. It could be any system we've now described by this linear system. If we want to know what's the sinusoidal steady state output, all the transients have now disappeared or gone away, and in that case we're saying how long is infinite, or what is infinity. If we're looking at the sinusoidal steady state, we're making two assumptions. If we excite a system with a cosine or a sine, and somebody says, what's the sinusoidal steady state output? We're really making two assumptions. What are those assumptions? When will you have a sinusoidal steady state behavior? Under one condition of your system. And there I'm sort of thinking right and left. Right and left. If you had a pole in the right half plane, will you have a sinusoidal steady state behavior? No, you'll have an unbounded response. You'll never get to a sinusoidal steady state. Your system will go unbounded, your output response. So you, one, have to have a stable transfer function. Your H of S, and to have a stable transfer function, all of your poles, we're not worried about zeros, the poles of your transfer function in the continuous time setting, all of your poles are in the left half plane. They have negative real parts. That's one assumption. The other assumption is that we've waited for all of our transients to disappear. And how long do we have to wait? 5 tau for our initial conditions to basically be gone. Question? Yes, so now what I'm wanting you to be clear on, the question was, where are we in the complex plane for stability? I think I'm paraphrasing, but is that close enough to your question? And what did you just say basically in your question? It depends. It depends if we're dealing with a continuous time system or a discrete time system. If it's a continuous time system, then we're in the S-plane. And for a system to be stable, we need all of our poles to have negative real parts or be in the left half plane. If we have a discrete time system, then we're playing in the Z-plane, and then those corresponding points, the poles of our transfer function, all need to lie inside the unit circle to have a bounded input, bounded output stable system. Is that clear? And now what we want to know is if we do have a stable system, all of our poles of either H of S or H of Z are in the stable region of the respective plane. For the continuous time case, we now simply walk up the imaginary axis to the location that we're exciting the system at, which in this example is a frequency of omega sub 1. We walk up j omega to that point, and we evaluate the transfer function at j omega 1. And if you have a calculator, some of them will actually evaluate that transfer function for a complex number. And it will give you a complex number, h of j omega 1. Again, this is the continuous time case. We find the magnitude of that complex number, or we just convert it to polar form, and we find its angle. And we use those two pieces of information to influence our input cosine as it migrates through the system. The system changes the behavior or the signal a little bit, does it change the frequency? If it's a linear system, if you shake it at omega 1, what's the output going to shake at? The same frequency, omega sub 1. No? Quit shaking. That's what I was just told. So we had a quick transient. Okay? The poles were quite far into the left half plane, weren't they? If that was an analog system. So now we had an amplitude of A for the input. That now gets adjusted by how the system responds at that frequency, which is given to us by the magnitude of h of j omega 1. And then it shifts it in time, and that's what this angle does. That's the phase shift. Question? So the question was, what happens when we have a pole and zero at the same place in the complex plane? And let me maybe answer that. This is now the S-plane. I'm now assuming that H is in pole zero form. And I'm now showing you one way to evaluate or find this complex number, h of j omega 1, graphically. I'm trying to get you visually thinking about what's going on. If you have, and hopefully this is somewhat clear, I now have 3 poles. There are 3 blue X's in the left half plane, so my system is stable. I have 1 real zero. Each of those factors give rise to a magnitude and an angle to the appropriate frequency, omega 1. We can measure that with a ruler or with our algebra. That's now our hypotenuse, isn't it? We have the real part squared plus the imaginary part squared, square rooted. That gives us our hypotenuse length, or the distance from that pole or zero to that frequency location. And that's what adjusts our magnitude of h of j omega 1, and that's what provides us with our angle h of j omega 1. Meaning, for this pole that's closest to the origin, that has a length to the frequency point j omega 1 of L sub p1. That's that hypotenuse. And that ends up being downstairs in our transfer function expression, and the angle theta p1 is the angle looking from the positive real axis up to that point. That's the angle theta p1. The question was, what happens if you have a pole and a zero at the same point in the complex S-plane? Do you see what would happen if I would slide that green zero on top of that blue pole that's real? What does that do in my expression for the magnitude and the angle? They cancel each other out, don't they? So they would then cancel each other out if you have a pole and a zero on top of each other in the complex S-plane or in the complex Z-plane. And that we will use when we're designing controllers later on in the semester. We may actually want to be canceling stable poles and zeros. What can we not cancel? Unstable poles or zeros. So what? Why? We'll get there in a little bit later in the semester. And it's really tied to, I think, homework problem number 2, or yeah, problem number 2 on homework number 1, which you probably didn't get that connection, but you were finding all these transfer functions. Each of those needs to be stable, and when you have an unstable pole zero cancellation, some of those actually may lead to an unstable system. Okay, so that's a quick answer to why do we want to cancel. We won't worry about that just yet. Just know you can't cancel unstable poles and zeros. And alpha is just the magnitude that's left over when you factored h into pole zero form. Is that clear? this should be a review. This is what you've already had in a class like ECE 320A, hopefully. What happens in the discrete time case? It's going to be similar. Now we have a discrete time sinusoid, which has an angle of theta, a time index of n, and let's say a magnitude of d for discrete time. And again, if we're shaking this system at a frequency with our argument theta of n, what's going to happen at the output? If it's a linear system, it's going to shake at the same frequency. But again, we need all of our poles where, if we're talking about sinusoidal steady state behavior. They need to be inside the unit circle. They need to be stable. This is now the discrete time setting, and our output will be adjusted. We'll have the original output D scaled by the magnitude of our transfer function at that angle. So we're evaluating H at that on the unit circle at an angle of theta, and we compute its phase, and that adjusts the offset in time of our cosine waveform. One thing I want you to be comfortable with is Euler. You're going to Euler, no. This is not a mechanical system, so we're not squirting oil onto the mechanical system, but here's Euler's equation, and what I'm trying to remind you of is if we're interested in e to the j theta, that has a magnitude of 1. Because what does Euler tell us? E to the j theta is cosine theta plus j sine theta. And you should remember that to find the magnitude of a complex number, it's the real part squared plus the imaginary part squared, square rooted. But that now leads to the magnitude of cosine theta plus j sine theta. So we have the square root of cosine squared of theta plus sine squared of theta. And we all remember that cosine squared plus sine squared is equal to 1. Right? That's a basic truth. And that tells us then that we're on the unit circle if we are evaluating our complex transfer function h of z when z is equal to e to the j theta. This diagram gets a little busy. This is now in the z-plane, but it's very similar to what I had in the s-plane. Now we find our angle. We get out our protractor and we measure that angle theta. And that tells us where we are on the unit circle. Then we find these lengths from these singularities, the poles and the zeros, to that point on the unit circle, and we measure each of those respective angles. And in some cases, they may be negative. Theta sub p sub 2 is negative. It's measured relative to the positive real line going out, well, positive real. It's going to the right in this diagram. Now in pole zero form, that's what h of z was in. I'm now assuming that we factored it and we have our zero factor and our pole factors, and a constant beta factors out. So we have to include that in our expression for the magnitude of h at e to the j theta. And if you were quick with your dividers and your protractor, you could compute this geometrically. You wouldn't have to calculate it or put it into your calculator, but if you have a nice calculator, you can simply plug in e to the j theta, where theta is some radian angle, and it will give you a complex number. And that complex number you'll now write in polar form. You'll find its magnitude and angle, and that's what you'll use to adjust the output that you initially had relative to the input. Questions on finding the sinusoidal steady state output? Take off my glasses. I apparently do not see any questions. Let's now look at what we did last time, which was apply this idea, this concept of a frequency response to a low-pass filter. I think somebody was trying to excite the classroom with an impulse hammer to see the initial condition response. All right. I may go look. I don't need to be mic'd if I go look, okay? You might hear more than pounding on. Never mind. Okay. Our RC circuit leads to a first-order differential equation, which now we have this time constant tau, which is RC. RC times V sub 0 prime plus V sub 0 t equal V sub I of t. We found the difference equation associated with that by approximating the derivative, and that led to this discrete time equivalent of a low-pass filter, which is a difference equation. And for our particular bandwidth of 100 hertz, roughly, that gave us a tau of 1.67 milliseconds and a sampling period smaller than that of 0.333, which those ratios provide us with then a value of our A matrix in this first order difference equation of 0.8 and our input matrix gamma of 0.2. Is that system stable? Can you see that from this first order difference equation? Yes, no. Do you know what I'm asking? Can you determine stability given what I've given you for that difference equation? Or, if you can't, can you from this transfer function? If you transformed that difference equation into the frequency domain and found this transfer function, which is this ratio of the output Z transform over the input Z transform, now it's in pole zero form. And what do you want to have happen for a transfer function to be stable in the Z domain, or for a discrete time system? What do you need to have happen for that system to be stable? All of the poles, not the zeros, the poles have to be inside the unit circle. So you're now evaluating that denominator, and you're finding all the values of Z that cause that denominator to vanish. How many values of Z make that happen in this example? We just have a first order, so we just should have one pole. And where is that pole located? 0.8. Is that inside the unit circle? We're just finding the magnitude of that complex number. This is a complex number at 0.8. Has no imaginary part. But it does have a length from the origin of 0.8, and that's less than 1. It is a stable system. And in this case, since it's first order, that's actually the eigenvalue of your A matrix. Here's your A matrix is just that 0.8. It's a 1-by-1 scalar in this example. If you were given a third order state space representation on the exam, and I said, is this system bounded input, bounded output? stable, question, what would you do besides sit on a table and make noise? How would you determine a third order state space representation difference equation, whether or not it's stable, if you had computing power available, brain power? What would you be doing in your state space representation? You can find the eigenvalues, can't you? And you want all of those eigenvalues, even if they're complex. Your calculator may not find them unless you say, I need complex roots. So you need to make sure on your crib sheet that you have the quadratic formula if your calculator will not compute zeros of a polynomial that has complex roots. But you would find the eigenvalues of that 3 by 3 matrix and check the magnitudes of each of those 3 eigenvalues, and if their magnitude is less than 1, then your system is stable. Here's where we were working last time. We injected into this low-pass filter, which is first order, an input v sub I of n with an amplitude of 2 and an angle in radians of 0.1665, or an angle of 9.54 degrees. And on the exam, I might ask something as maybe straightforward as, what's the structure of v sub 0 of n? Maybe not what is v sub 0 of n in the steady state, but what's the structure? How would you answer that question? What is the structure of the time domain sinusoidal output? Let me say this. In the steady state. What's v sub 0 of n? What's one part of that that you know has to be true? It's a linear system, and we're exciting it with a sinusoid. You better get a sinusoid out. And what's the frequency of that sinusoid that you get out? The same frequency that you excite the system with. And in this case, in the discrete time setting, that's this angle, theta, which I might label as theta sub d. Earlier, I just called it theta. But now we know that we're going to have the original amplitude of our input scaled by the magnitude of that system at that angle, theta sub d. You said it needs to be at the same angle as what we were injecting, and it will be offset in time based on what the complex number is that we evaluate, h of e to the j theta, what its angle is. Now, to find this magnitude and phase, how do we do that? If we actually want to compute that sinusoidal steady state output, how would we compute it? How do we evaluate or find the complex number h of e j theta sub d? Where is that in general? It's on the unit circle. And where on the unit circle is it? It's on the unit circle because we're evaluating it at z equal to e to the j theta sub d. And we know that has a magnitude of 1 because we have cosine squared plus sine squared is equal to 1. we have h of z. How do we convert that into a complex number that will give us this magnitude and angle information? Can we assign z to a particular value? Somewhere on the unit circle. And I just gave it to you, did I not? It's e to the j theta sub d. And what's theta sub d? I hope that on exam day on Wednesday that this comes a little bit quicker than what you're demonstrating tonight, these answers. Or I won't have much work to do grading these exams. Yeah, it depends on the probability of it getting graded. If you don't put anything down, it's easy to grade, even without flipping the coin. So what's theta sub d? That's that angle in radians. That's this 0.1665. And if you're computing this on your calculator and it's set to degrees, you need to make sure that you're doing the right evaluation. Or this is now 1 at an angle of 0.1665 radians. So everywhere we see a z in h of z, we replace it with that complex number. The numerator didn't have a z. It just had 0.2. The denominator had a z minus 0.8. And now, what do we invoke to move further? We're trying to find a complex number for h of z with z equal to e to the j theta sub d. How do we move any further? Now we invoke Euler. Euler allows us to change that complex exponential into a real or into rectangular form, a real part and an imaginary part. Euler says we have cosine of that angle plus j sine of that angle. And if we make those computations, we now have a real part of 0.9862, which if our angle was 9.5 degrees, it's not going to be very much different from 1, is it? It's on the unit circle, and it's just 9 degrees beyond the point 1, 0. And our imaginary part, or component, is j 0.1657. And if we combine the real parts in the denominator, and a lot of times when we want to multiply and divide with complex numbers, we like it to be in the polar form instead of rectangular form. We can convert that rectangular form of the denominator into a polar form. And we have then a magnitude of 0. Or a hypotenuse of 0.2492 at an angle of 41.676 degrees. We have 0.2 divided by something that's a little bigger, 0.25, which is roughly 0.8, and an angle of minus 41.676, and now that's in degrees. That's now our complex number in polar form that we can use to find our sinusoidal steady state output. We now have V naught steady state of n is equal to 2 times the magnitude of h of z at that on that unit circle, which is 0.8, cosine of 0.1665 in minus 41.676 degrees. Or this is now 1.6, so it's a little bit less than 2. We've collapsed it a little bit in magnitude. It's at the same frequency, and it's just shifted a little bit or delayed in time by that phase shift. And this is true for n greater than or equal to 0. Do you see the picture in the z-plane where these numbers might have come from? Our pole was at 0.8. Now this will be testing my sketching skills, but here's our unit circle. That's supposed to be a unit circle. Where are we evaluating on that unit circle? At an angle of 0.1665 radians or 9.54 degrees. Let me just say that that's right there. That's our e to the j theta, which we calculated to be this number in rectangular form. So this point is now 0.9862 plus j 0.1657. And how do we use that information? What's the distance from that pole to that point? What were we calling that before? L sub p. That's now this particular distance. This length is L sub p, and this angle is our theta sub p. And what is L sub p? You could measure it if your drawing was accurate, or you could say, oh, it's all the way over to 0.9862 minus 0.8. It's that real distance. And the vertical distance is just that 0.1657. So that now we wanted to find this that's the real part of that hypotenuse. The vertical part is the 0.1657, and that ends up being this 0.2492. That's what's in the denominator. And our angle, theta sub p, is the inverse tangent. What's the argument of that inverse tangent? It's the vertical distance over the horizontal piece, and that horizontal piece is the difference between the 0.9862 and the 0.8. Or this inverse tangent is now 0.1657 over 0.9862 minus 0.8. And that was our 41.68 degrees. Question? Oh, I'm sort of mixing apples and oranges. The question was, should there be a square root there? I can change that by doing this. I wanted the magnitude of that expression. So now I have the real part plus j, the whoops. Boy, I was really mixing apples. I was having apples and bananas, wasn't it? So that's now the complex number, but now I could find the real part squared, the imaginary part squared, add those two and take the square root. And that should give me the length of 0.2492. Thank you. Other questions on that? But do you see how maybe quickly that would be computed if somebody gives you this transfer function, h of z of 0.2 over z minus 0.8, and they give you this input? Now you just go to that z-plane diagram, measure that length from the pole to the unit circle, given by the angle that we're exciting the system at, the 0.1665, and measuring that angle or computing it with your trigonometric relationships concerning an angle and the length. Will you be able to do that on the exam? If I shake a system at a given frequency, at a given angle in the discrete time setting, you should be able to now figure out how that modifies or is modified as it passes through that linear system. Questions on that? Let's look at the ROC. The region of convergence and stability. And for starters, let's go up to 30,000 feet and get the big picture view of this concept. And this is needed, the region of convergence is actually needed to allow us to go from a Z transform back into the time domain. To do the inverse Z transform, we need to know what's the region of convergence. That's when this becomes important. And one thing that I would like for you to leave tonight with in terms of information is the fact that the region of convergence, the ROC, is actually determined independent of any stability considerations. So the ROC is determined independent However, a signal is bounded, or a system is stable, if the corresponding region of convergence actually contains the unit circle. And that will become a little bit more clear in this discussion. You find the region of convergence, and if that actually contains the unit circle, then whatever signal or system you're dealing with is bounded or stable. If the region of convergence does not contain the unit circle, if the unit circle is outside of the region of convergence, then you have an unbounded signal or an unstable system. Question? So the question was, what happens if the region of convergence contains part of the unit circle? I think that was the question, and that should never happen. So it will either contain the entire unit circle or none of the unit circle. Here's a fact that might help with that. If we have a system, the poles of that system never lie on the region of convergence. They're always at the boundary of the region of convergence or outside the region of convergence. The poles never lie on the ROC. I said we were going to go up to 30,000 feet. So let's now look down and look at the patterns that are possible for ROCs in the complex Z-plane. And actually, this isn't hard. There will only be 3 different patterns. 3 patterns for the ROC. Possible ROC patterns. And these patterns are independent of stability. Let's look at pattern number 1. We're going up high, and now we look and we see that we have some poles, and these should all be complex conjugates. And let's say we have a pole there, and our region of convergence now, that's supposed to be a circle, and it's outside the furthest pole, and our region of convergence is out here. This is our Z-plane. Here's the real part of Z. Here's the imaginary part of Z. And this is our picture from 30,000 feet. We have a cluster of poles, and our region of convergence goes off to infinity. It's unbounded, but it's outside of our poles. Those poles do not live or lie on the shaded region. Is that clear? So here you could say that we have an unbounded, that region of convergence goes off to infinity in all directions. Unbounded region of convergence, let me say with a central pole or void. That's one of the patterns. And the description that I will use, and hopefully this is clear, we could describe this 2 different ways. Let me say the A way, and this doesn't refer to grades. This is just option A or option B, not an A grade or a B grade. The first one is that the region of convergence, the ROC, lies beyond all poles. That's one way that you could verbally state this picture. The region of convergence lies beyond those poles. Or another way to try to describe that, the B way, is that we could say all poles are interior to the ROC. Now, if we have this kind of a picture in the z-plane for our region of convergence, that now tells us something about the sidedness of our time domain waveform. The implication is that the time domain waveform x of n corresponding to this region of convergence is right-sided. Meaning, if we now are in the time domain and this is x of n, we don't have any signal in the negative half of the time axis. All we have are signals here. 1, 2, 3, 4. It's defined on the right side of the time axis, to the right of the origin in n. That's what I mean by a right-sided x of n. And whether those are bounded or unbounded is going to depend on where those poles are located. It doesn't depend on the picture that this region of convergence is outside all of our poles. If all of the poles are actually inside the unit circle, then these would be bounded. If one of those poles is outside the unit circle, then we would have an unbounded behavior. Or we could say that x of n is equal to 0 on the left side, or for all n that are negative. We will justify this implication in a minute, but now I'm just wanting you to get the big picture. If you have an unbounded region of convergence, you have a right-sided time domain sequence. What's another pattern? Let's look at pattern number 2. At 30,000 feet in the z-plane. Suppose now that that's the region of convergence. And I haven't labeled the radius of that disk. It's not the unit disk necessarily. My poles, let's say there's one there, there's a 2 here, maybe there's some here, but the region of convergence is interior to the smallest pole. Do you see that that's a different pattern than the first pattern? This one is bounded, this region of convergence. For the region of convergence. How can we describe this? We have an A way and a B way. Here, the A way would say that the region of convergence lies inside all of the poles. Or the B way is to say that all poles are exterior to the region of convergence. You see that this region of convergence is really the opposite of this region. The first region was unbounded outside of a disk. The void was the disk. Now the region of convergence is that disk. And we don't have anything region of convergence-wise going unbounded. It's now bounded. If this one's just the opposite, what could you maybe guess in terms of implication for where this time domain waveform would be defined relative to n. Or what sided would this x of n be? If the earlier one was right-sided and this is just the opposite, it's left-sided. Somebody's still awake. X of n is left-sided, or we now could say that x of n is equal to 0 for all n that's non-negative, or if we were sketching our time domain waveform x of n, now we have values at -1, -2, -3, negative values of n. And again, whether those are bounded or unbounded will depend on if this disk actually contains, or if the unit circle is covered up by that region of convergence. Was there a question? So now the left-sided, I'm going to exclude. The question was, does it have to be 0 at n equals 0? I'm going to exclude the origin. I'm going to say this is for exclusive negative arguments of my time domain waveform. That's pattern 2, and I promised there were 3 patterns. Question? So now the question was something about running backwards, and I don't want to run backwards. I might fall down, but we won't do that, meaning we'll talk about right-sided and left-sided and stick with the appropriate regions of convergence. Actually, I used to be pretty good at running backwards, but we won't go there. Pattern 3. What do we think this picture looks like? This is still the z-plane. And this one you could think food. We always have to have a food theme at some point during the lecture. How do we put food into a pattern? We had sort of a disk, which could have been a cookie, right? Or a pie. The unbounded, we better not talk about food with unbounded region of convergence. But what would this one be? A donut or a bagel. So now our region of convergence is annular or donut shaped. Now this is our region of convergence, and our region of convergence is always bounded by poles. So we could have some poles inside this void, and we could have poles outside that region of convergence. This picture now we will call annular, or donut shaped. And the description is the ROC is annular or donut shaped. Or B, some poles are interior to the region of convergence, and some poles are exterior to the region of convergence. So our region of convergence is really, it doesn't include the origin, and it doesn't include infinity. It's a tube, or it's annular, or it's donut. What's the time domain implication for this region of convergence? We had right-sided, unbounded region of convergence. We had left-sided, bounded region of convergence. Now we have annular. What do we think? Now it's in both sides. It's two-sided. We can have a waveform that's defined for negative ends and non-negative ends. X of n is a two-sided sequence, or X of n is non-zero, for n greater than or equal to 0 and n less than 0. Or now we could have, these are supposed to be uniformly spaced. In terms of distance apart. Our capital T, or the sample period, is the same. That's now a two-sided waveform. What do we have? Do you understand the three different pictures? Pardon? You're not going to have a fourth region of convergence. You have one that's unbounded, which includes z equal to infinity. We have one that's a disk that includes the origin. And we have a region that's annular that does not include the origin or infinity. Question? So the question was, will the ROC always be centered on the origin? And the answer is yes. It's always going to be centered at the origin in the z-plane. So let's look at some details. All of these details are motivated or found by looking at the z-transform. And this you should know for the exam. What's the definition of the z-transform? How do you define the z-transform? If I gave you a sequence, little x of n, how would you write the z-transform expression? I've already given you half of the answer. I've given you the summation symbol. You take that sequence and you weight it by this complex number, z raised to the minus n. And where do you sum over? In general, we need to go from both minus infinity and plus infinity. Or we're now going to be looking at, coming up from the left, we will have x of minus 2, z to the minus minus 2. That gives us z squared, plus x of minus 1, z to the minus minus 1, there's z, plus x of 0, z to the minus 0, or 1, plus x of 1, z to the minus 1, plus x of 2, z to the minus 2, etc. Now, just looking at this, can we understand where the implication comes from in terms of if I give you a region of convergence pattern, can you, just by looking at this infinite expanse or this series, can you tell me which terms have to be zero and which ones could possibly be non-zero? What if the region of convergence contains an infinite value? We have x of minus 2 raised to the z squared. We're raising infinity to the, or we're taking infinity and squaring it. If this capital X of z is bounded or well behaved, what do we know about little x of minus 2? If it's supposed to be weighted by an infinite value, it has to be 0, doesn't it? What about x of minus 1? It's raised to this, or it's scaled by infinite, or infinity. So what's x of minus 1? 0. What's x of minus 3? That's infinity cubed, scaling x of minus 3. If our region of convergence contains infinity, if it's unbounded, what does that tell us about the negative indexed time sequence values? They have to be 0, which means we can only have a right-sided sequence. Is that what we said before? This pattern contains z equal to infinity. It's unbounded. Looking at this definition of our z transform, and if it's well behaved, that means it sums to a finite number, then that implies that we cannot have any time sequence with a negative argument in n. This will make sense if it's not yet, but hopefully it will start to make sense. Let's go the other way. Suppose we looked at this curve. Z now could be equal to 0. Yes? 0 is a part of our region of convergence. What does that mean in this expression? If I look at x of 1, and now I'm going to have to reclaim or restate what I said before. Now let's go ahead and include the n equals 0 case in this. It's okay to include it, but if I now have z equal to 0, what happens when I look at 1 over z? It blows up, doesn't it? What if I look at 1 over z squared for z equals 0? It blows up. Every term on the right, or every term that's scaled by a positive indexed argument on the waveform, can't be there, can it? We cannot have x of 1 non-zero, x of 2 non-zero, so we have to have a left-sided sequence. If every one of these terms is well behaved, or if we now have a region of convergence that does not include the origin, it doesn't include infinity, and it's bounded, then we can include both sides of our time domain sequence. We can have negative arguments or indices and positive indices. It can be a two-sided waveform. That's where this is coming from. That's how these implications arise, but now if I give you the following, this is trying to motivate the region of convergence. I want you to be thinking about this weekend. You won't think about it between now and the exam. You'll be focused on exam number 1 material, hopefully, and if you have time, you can think about something else. But now what I want to ask is, if someone which you could think the instructor, if the instructor gives you capital X of z equal to z over z minus 1/2, what can be said about the time domain waveform? How do we get the inverse Z transform? And the short answer, just to give you the answer in the back of the book so that you know what to look for this weekend when you're looking at this and discussing it with mom and dad, the region of convergence and sidedness is the following. We don't know whether this is a right-sided or a left-sided little x of n until somebody tells us what is the region of convergence. Having that transform is not sufficient information. We also need to be given the region of convergence before you can find little x of n. And we'll pick up at that point in a week.